Yeah, welcome to the Theory Lunch, and we are very, very happy to have Chris Musco. We go long ways back. We were postdocs together in this department long time ago.
Doesn't feel that long ago.
You
It
know,
is,
some
it is,
years,
yeah. Yeah.
many years ago, some years ago, only a few years ago. And yeah, Chris does amazing work. He's been doing amazing work in numerical linear algebra, graph algorithms. And I guess you are the associate professor. You're an associate professor, time flies.
Yeah, as of
Yeah.
this year, yeah.
Yeah. He's an associate professor at NYU Computer Science. He's been doing great work in graph algorithms, numerical linear algebra, sketching, streaming, etc. And today he's going to tell us about something super important both in industry and in theory.
Yeah. Yeah, thanks so much for having me. It's nice to be back. Yeah, today I'm going to be talking about something that's definitely more along the lines of like theoretical computer science. I know some people here are like uh, more of my linear algebra friends. There's going to be no linear algebra in this talk. This talk is about something called navigability, and it's a topic that I'm really interested in right now called graph-based nearest neighbor search, graph-based vector search, or also graph-based nearest neighbor search. So I'm going to try to introduce that topic like sort of slowly, give everyone a picture of what's going on. Should I hide this or it's okay, I guess. I'll put it on the top right. Oh, sorry. Yeah, I'll introduce this topic slowly. Some people will be very familiar with it, but I think it's just good to have everyone on the same page. And then I'm going to present a couple results, which are joint work with a bunch of people at NYU, in other places, Cornell, UMass, University of Maryland. We've been interested in these topics, so yeah, we've got a few papers on this stuff now, and I'll explain a couple nice results to you. Okay, so the problem we're studying, it's a very basic problem. It's the nearest vector search problem. The setup here is you have some database of vectors, and I think of those vectors, which I'm calling x1 through xn, it's a very large database. So, it could have a billion vectors in it. That's like a typical size in an industry application. And the vectors are like long, they're high dimensional, but they're not insanely long. Like there might be hundreds to thousands of dimensions. And the goal of this problem is you get in a query vector, which has the same dimension as your database, and you want to find the closest vectors in the database with respect to some distance function. So typically you would try to find the k closest vectors for some parameter k, and you can pick any distance function you want. For the purpose of this talk, let's just always think about it as Euclidean distance because it's easy and it's widely used in practice, but nothing I'm going to talk about is actually specific to Euclidean distance at all. And also for the purpose of this talk, let's just say we're interested in the k equals 1 case. We want to find the single nearest vector to Q in the database. Okay? Why does this problem come up? I mean, it's been studied a lot. It's been studied in the theoretical computer science community for a very long time, like in low dimensions, very long time, in high dimensions since like the late 90s. So many people have learned about this problem, but it's received renewed attention recently because it's the main driver behind what I would call AI-based search. So what is AI-based search? Typically web search, or it has been typically based on keywords. You search for something in Google, what's the best dim sum in New York City? What does Google do? It looks for web pages where those words appear somewhere on the web page, and then that is it's how it pulls things and does some sort of re-ranking. Even when you're doing Google image search, the primarily way that Google image search was worked for years is based on text, on keywords. What they would do is you look at an image and you look at text surrounding the image. So like in the alternative description of the image within the HTML and text around where the image appears in the HTML. And that text guides what's pulled into image search, which then does some re-ranking. Some machine learning was going on within like the past 10 years. I won't talk about it, but like roughly that's how the big picture happens. There's been a huge paradigm shift in search in like the last 5 years because machine learning models for embedding data into vectors have gotten better. So the dominant procedure now is actually quite different. What people are doing is they're using embedding models, BERT, CLIP, there's tons of these models out there, which take media in. That media could be anything. It could be an image, it could be a sequence, it could be a document, it could be like a text description, it could be a document with images in it. Feed it into a big neural network, and then that spits out a high dimensional vector representing the image. And the hope is that you train that neural network in such a way so that semantically similar objects map to semantically similar location, like map to similar locations in the high dimensional vector space. So these are all pictures of dim sum. All those pictures map to roughly the same place. A picture of a dog would map to somewhere different. And the nice thing is a lot of these models are multimodal. So how do you do search? You just feed in what you're searching for, dim sum, to the same model. You get spit out a new vector, which, if it's semantically similar to these images, should appear nearby those images in the high dimensional vector space. And then you see where vector search comes up. I want to find the vectors in the high dimensional vector space, which are closest to my search query, to return my search results. So, like, yeah, AI-based search in this way is starting to be used super widely. So it's now dominating how image search works. Email search, like all Microsoft Outlook, if you have a Microsoft Outlook account, that's using vector search, even just for text search. It's using keyword and vector, but it's incorporated. So there's been a lot of focus on this problem in recent years. Okay, so yeah, because we have these great modern embeddings, we've reduced the task of search to this very simple geometric problem. High dimensional set of vectors, you get in a query, find the vector that's closest to your query. Unfortunately, that's like a simple problem, but this is a notoriously hard algorithmic problem. So in general, the only way to solve this problem, if you're just like given it up front, is to scan through the database. I need to read my data. So what do? I scan through my list of n vectors. They're all in d dimensions. If I have a standard norm like the Euclidean norm, it takes d time to compute the distance. So the total time to do what we would call a linear scan over the data is n times d. The d dependence is fine. The n dependence is really bad because in like real application stuff, n is on the order of a billion. So doing the linear scan is just completely infeasible. Okay, so how do you do better? The only hope for doing better is if we allow some pre-processing. So the idea is you're going to take your set of vectors, you're going to pre-process them into a data structure, and then hopefully you're going to be able to use that data structure to answer these queries faster. So you invest some computation up front, you might invest some additional space, you store some stuff in addition just to the vectors, and then because of that, you can answer these queries faster. Okay, so many people have seen this, but if you haven't, you still definitely know how this works because you know how it works in one dimension. If my points lie on a line, how do I pre-process the points to get efficient search? I can build a binary search tree over the points. It will have depth log n. So searching, given any query, if I want to find the nearest point to it on a line, you can basically do a binary search. It takes time log n. And the binary search tree only has space complexity order n. So you just had to like store a tree. And the pre-processing time is also efficient. You have to sort the points to build a binary search tree. Okay. So in one dimension, you know how the drill pre-process, you get log n times search. In two dimensions, you can do similar things. So in two dimensions, you can build like data structures based on Voronoi diagrams. Similarly, you can do order n space and log n times search. As soon as you hit three dimensions and above, you start picking up some dependencies on the dimension. So either the space complexity of tree-based methods, they're the classical techniques for this problem, needs to grow exponentially in the dimension d, or your search time needs to grow exponentially in the dimension d. And d wasn't huge, it might be 100, but if you're getting something exponential in d, that makes these sort of like tree-based methods and their generalizations completely infeasible. Okay. Yeah, this is even the case if we allow approximation. So I'm going to, in general, allow for approximation, which makes the problem easier. Instead of just trying to find the nearest vector to Q in the data set, let's even allow ourselves to relax the problem. You have some constant C, which is greater than 1. This is your approximation factor. It is okay if you return an xj, that is, its distance from Q is no more than C times the nearest vector in the database's distance for Q. Even in that case, these methods will grow exponentially. Okay. So where does this leave us? Well, fortunately, there was like some really amazing work on this problem roughly 20 years ago. Indik Motwani introduced this method called locality-sensitive hashing. There's a lot of other techniques, a lot of other just floating around at the time, but this is the method that I think is credited with first breaking what we would call the curse of dimensionality for the nearest vector search. Okay, so what is locality-sensitive hashing? Probably some people have seen this, some people haven't. It's a really simple algorithm. It's like a great algorithm. I teach in my class because it's easy to understand. Some work goes into analyzing it, but the idea is beautiful. You do the following. You have points in high dimensional space. You basically pick a bunch of random hyperplanes. And for each hyperplane, you check which, so say this is my query point. You check which side of the hyperplane the point lives on. Okay, so like for the first hyperplane here, I might say, oh, it lives on this side of that hyperplane. For like this hyperplane here, I might say it lives on this side of that hyperplane. You do that for all your hyperplanes. Each of those checks only takes order d time because you just need to do an inner product with your orthogonal vector of the hyperplane. And what it does is it pins your query down to a region in the space that is the intersection of all the half spaces that your point lives in. And what you did in your pre-processing step was you pre-computed all of the points that live in the same region. Basically, create a hash table for every region. You store the points that are in the region. And to answer our nearest neighbor query, you only return the smallest distance amongst those points that live in the same region. Okay? So it's not an exact algorithm. Actually, even in this case, it might miss this point. That point is the nearest neighbor to our query, but it's on the other side of a boundary. But that's unlikely to happen. Right? Your close by points are much more likely to lie on the same hyperplane as you are. So in general, this is good at finding good approximate nearest neighbors, especially if you do some sort of like repetitions. Okay, does that make sense? Okay, so yeah, you can prove really amazing theoretical guarantees for LSH type methods. Here's a sample result from Fox 2006 that was proved by Andoni and Indyk. This is specific to the Euclidean norm, which is why I'm picking this one. You can claim that for any approximation factor c greater than 1, I can find an approximate nearest neighbor, so within a c factor of optimal, in O tilde of d times n to the 1 over c squared time. And you do this with a data structure whose space is, I need to store my original data set, of course, and then space that's a little bit super linear. So it's like n to the 1 plus 1 over c squared. Yeah.
So how do we know what points have the same cell? This is the processing, so do we fix the random isolation?
Yeah, exactly. So you fixed in the pre-processing, you fix the random hyperplanes, and then they stay fixed for like the lifetime of how you use the data structure. Yes, this is with high probability. And you can, it's with high probability over the query points. So like it's not, you could find query points that the data structure would fail for, but if the query points don't know about the randomness of the data structure, it succeeds with high probability.
But there is also randomness in how the isolation works, right?
Yeah, that's what I mean by the randomness of the data structure. Yeah. Yeah.
So what's the time complexity of building the data structure here? Like how many hyperplanes are you using?
It's like slightly it's like a small polynomial in n. So the time complexity is roughly this. It's like a little bit more than linear time complexity. Or it must be d times that or something. Yeah. Yeah, good questions. Any other questions about this data?
Yeah, actually one quick question.
Yeah.
So just to get a sense of whether this is somehow typical or worst case.
Yeah.
If I were to start with points and then let's say, think of a smooth version of the problem where like, every point was perturbed a little bit.
Yeah.
And then I asked what the time complexity is. Would it substantially improve or would it basically be?
I don't think it really improves, although I'm hiding it. There's a dependence here on, okay, there's some details here. I'm hiding a dependence on the aspect ratio of your data set. So if you technically have a logarithmic dependence on the distance between the furthest points and the distance between the nearest points, that is something people care about removing. And perturbing would get rid of that. But I don't think it would change I don't think you would get a better complexity beyond just assuming that your points weren't super close together. It's surprising that aspect ratio. I'm not going to explain why that aspect ratio shows up, but it's a little bit weird. Yeah, but I don't think perturbing substantially changes. This is a really amazing result. So like, think of the setting when C is 2. C is 2 is reasonable because the way that people use this stuff in practice is they're not really just returning one nearest neighbor. They're returning like 100 or 1,000 nearest neighbors, and then they're re-ranking them using some other algorithm. So like, you don't really need to be that precise. You just like get a bunch of pretty good stuff. So in the setting when C equals 2, 1 over C squared is 1/4. So the runtime here is like n to the quarter is how it's scaling, d times n to the quarter. Even if you have a data set of size 1 billion, n to the quarter is less than 200. I mean, they're hitting constants here. There are logarithmic factors, but like the scaling there is like pretty amazing what they're getting from these LSH methods. And it's not just that they work well in theory, they also work quite well in practice. So like a lot of this early work on LSH was awarded the ACM Theory and Practice Award. And what people were using in practice up until recently, that's where the talk's gonna come in, were basically like versions of LSH if you squint a little bit. So in particular, people in practice still like were using, or a very dominant approach is what I would call a space partitioning method, which is exactly of the same flavor as this. But instead of choosing my hyperplanes totally randomly, I choose them in some data dependent way. So by far the most common way to do this is use k-means clustering. You k-means cluster your data points, that gives you a bunch of centers. And those centers define separating hyperplanes, basically the hyperplanes that show up in the Voronoi cells. And the way they do the search is the same thing. You check, a query comes in, you check what center it's closest to. That's equivalent to checking what region of the space it lives in. And then you return the best option from that cluster center. So if you look at like the main libraries for nearest neighbor search at Meta or Google, they've been using nearest neighbor search for internal applications for a long time. They're based on techniques that you could basically view as like data dependent versions of LSH. So they work really good in practice. Yeah.
Are there any theoretical guarantees for these things?
No, as soon as you start, well, okay, yes and no. The algorithms they use were used k-means clustering. There's no theoretical guarantees for those, and you can come up with simple examples where they break. But within the theory community, there have been people who are interested in studying data-dependent LSH. And so people like Alex Andoni, Piotr Indyk, Huy Nguyen, Ilya Razenstein, there's work from like roughly 10 years ago where they show there are ways to choose the hyperplanes in a smarter way that can actually get you better runtime than like choosing them totally randomly. But those techniques they use don't look exactly like what people do in practice. But it's at least something like. Okay. So, okay, I spent all this time telling you about LSH methods. What's the state of LSH methods today? Within the past 5 years, there's like literally a multi-billion-dollar industry has arisen around just this problem of vector search. So there are startups like Pinecone is a large one based in New York City that are just selling a product which is vector search as a service. You have data set at your company where you're trying to create a huge database for like RAG retrieval for LLMs. You offload the search process to one of these companies' managed solutions. So a ton of companies are working in this space. And any company that does data management now has some vector search thing built into it. Elasticsearch, which is like the most widely used thing for business search, has vector search built into it. MongoDB has some algorithm for vector search built into it. What algorithms are all of these companies using? Surprisingly, most of these places have been around for 5 years or less, or their vector search products have been around for 5 years or less. Very few are relying primarily on space partitioning methods. So we've seen this crazy shift where like 6 years ago, everyone using space partitioning. These days, some people are like the big incumbents, Google, Meta, but a lot of people aren't using those methods. They're instead using a newer set of techniques called graph-based search methods, okay? Some of the common names, there's a whole class of these methods. I'm going to sort of explain how they're unified. There's something called like the navigating spreading out graph method. A really popular one is the HNSW method, which stands for hierarchical navigable small world graph method. Microsoft, all of their vector search is based on a graph-based method called DiskANN. I'll explain how they're unified. I should say these methods are like sort of new. Actually, similar techniques were studied in the early 90s for the low-dimensional version of the problem. So people have been looking at these techniques for a long time, but I guess they've had a resurgence of interest for the high-dimensional problem in recent years. And even before the 90s, a lot of these methods are inspired by research by Stanley Milgram and others in the 1960s on what people call the small world phenomenon, which I won't go into like the details of that, but if you want to ask me about it offline, it's really interesting. Okay, so what is graph-based nearest neighbor search? Oh, I was going to use some more pictures, then I'll tell you what it is. These things are being used widely in practice. They're also topping all the benchmarks. So nearest neighbor search is the type of thing where machine learning people care about it. So there are really good benchmarks out there. There's like a standard benchmark on GitHub. All the top scorers, you can't see it in this picture, I'm sorry, are graph-based methods. And there are two big competitions at NeurIPS 21 and NeurIPS 23. And for both of those competitions, the algorithms that topped the leaderboards were all graph-based methods. Okay, so what are, thank you. Okay, we're going to tell you what they are in a second. What was I going to say? We don't have guarantees for these methods. This is a theoretical computer science talk. So what I want to get across to you is a big difference between these methods and LSH is they work really well in practice, but we have very, very few theoretical guarantees. Some stuff is starting to be proven, but we don't understand them nearly as well. And this is a really nice open theory challenge. Like suddenly we have these new methods, algorithms that are faster than the ones that we have good theoretical guarantees for, but we really don't have a good theoretical understanding or explanation for that. So that's what I'm focused on in this line of work. That's what we're gonna try to like get a taste of during the talk. Okay. Yeah, so in particular, I said there's been some work. I'm not gonna talk about this in detail. There's been a lot of work on trying to analyze graph-based methods in restricted regimes, like you assume your data is random or in low-dimensional space. There's a lot of interesting ideas in that work, but I don't think it gives us a satisfying answer to why these methods work well for high-dimensional unstructured data sets. Today, we're going to sort of take a different approach to some of that work. I lost my slide. That's why I kept wanting to present it. It somehow got deleted. When am I going to tell you what a graph-based method is? Okay, I gotta just draw it. Let's see, how do I insert? I'm gonna draw it here because I have a blank space and then I'll delete it. What is graph-based nearest neighbor search? I knew it was coming. I just deleted the slide. The setting is as follows. You have your points. These algorithms are all ridiculously simple, which I love them. You have a set of points. What do? The pre-processing step is you don't do any hyperplanes, you don't do any space partitioning. The pre-processing is you build a directed graph over your set of points. Okay? So like some edges, it's directed. Let's see. Okay. And then what you do is a query comes in. Let's say the query goes here. And you pick some start node. Usually they just have some fixed start node. Let's say that's the start node. You look at that query and you greedily route to the query along the edges in your graph. So you start at the start node and you just look at your out neighbors. And you say, which of my out neighbors are closest to the query? In this case, well, I made this graph uninteresting. Let's get rid of this edge. Let's put this one in. I have two out neighbors. This one is closest to the query. So you hop to that node in the graph. Then you look at that node and you look at its out neighbors and you say which is closest to the query. Then you hop to that node in the graph. This one you look at its out neighbors and maybe let's say it has another one here. It doesn't have any out neighbors. This is the query here. It doesn't have any out neighbors that get you closer to the query. So your greedy search stops and you just return that as your approximate nearest neighbor. Okay, so here it wasn't perfect. This nearest neighbor was better, but the hope is that it gets you to some local minimum on the graph, which is like a pretty good nearest neighbor. So the idea is just build a greedy graph, build a graph, choose a start node, and then you just run greedy search till you can't get closer to your query. That's what all of these methods look like. The way they differ is mostly in how they build the graph. And there's some small differences in how they do the search, but think of it as just the standard search. Okay, does the type of method make sense? Okay, so now I can go back to, what we're gonna talk about. There's been some work on analyzing methods in like low dimensions, under data assumptions. I wanted to discuss connections between graph-based search and a concept called graph navigability. And then I'm going to talk about work on constructing sparse navigable graphs. So graph navigability is going to be a desirable property for the search graph we want for graph-based nearest neighbor search. And then I'm going to talk about some theoretical work on understanding, do these graphs exist and can I construct them efficiently? By the way, when do we actually go to? 120, okay. Okay, so let's go back to talking about the problem we want to solve. So we want to solve the C approximate nearest neighbor search problem. I don't need to erase that because it's not going to stay on this side. This is the problem we want to solve, C approximate nearest neighbor search. You get the query in, you return something in your database that's C competitive with the closest thing. I want to think about a really extreme version of that question. Suppose there are no duplicates in my data set, which is reasonable. You could usually just remove them. What if my query Q was in the data set? So Q actually equals xj for some j. Then, no matter what C is, it's number greater than 1. The minimum distance here is 0. So to solve the C approximate nearest neighbor search problem, you at least need to return xj, right? So a property of this is when Q is in the data set, you need to return the Q. And a natural question here is people are constructing these graphs. They tend to work well in practice. Can we at least construct a graph that's guaranteed to solve that problem? So make sure that if our query is in the data set, we at least solve it. That's where this definition navigability is. In addition to that, one such graph would be the complete graph. At the first step, you check all possible nodes, and then you just find X. We don't want the complete graph. We want graphs that are sparse. And ideally, when you find a point, a Q in the data set, it should take a small number of steps. Because what's the runtime of this algorithm? At every step of the greedy search, I basically need to compute the distance between my query and all of my out neighbors. So the runtime of the algorithm roughly scales as the out degree that could differ between nodes, but let's assume it's sort of uniform, times the number of steps I have in my walk. We're going to be really focused on that term. So it's really, really important that these graphs are sparse. Another reason it's important they're sparse is like you can't afford to take up a lot of space in practice. Okay, so the notion of navigability follows exactly from this motivation. We say a directed graph G over a point set x1 through xn is navigable if for all I and j, I is going to be my start node and j is going to be my target node. If I start greedy search on a graph G with start node I, and I query with xj, which is the vector at node j, then I will properly make it to node j, I'll actually return j. That's the notion of what navigability is. Does the definition make sense? So we didn't invent this property. Like, if you notice from earlier, actually, a lot of the techniques I mentioned, hierarchical, navigable, small world graphs, navigating, spreading out graphs, they literally have navigability in the name of the algorithm. And the papers discuss navigability as a desirable property. But none of these papers actually produce navigable graphs. They sort of use it as like a guiding principle. But at the end of the day, they construct a heuristic search graph using all sorts of interesting ideas. But they don't actually know that heuristic search graph is navigable. And the starting point for this work was, do sparse navigable graphs even exist? Like, or is it possible to come up with data sets where the complete graph is like the best you could do for navigable graph? And moreover, even if they do exist, if there are sparse navigable graphs for practical data sets, can we find them efficiently? So you give me a data set, you promise me, oh, there is a sparse navigable graph for it. Can I find that graph efficiently? So those are the two questions we're going to be talking about. Yeah, I'm interested in this property. It doesn't solve the whole nearest neighbor search problem. It's just a minimum necessary condition. It's not a sufficient condition, right? So like, even if you have a navigable graph, it might fail on queries outside the data set, but certainly you need this property. So that's why it's natural properties. Okay, so what is known about navigability? As I said, some of these methods were studied in the early 90s in low dimensions, and stuff is known in low dimensions. So in 2 dimensions, it's easy to show that the Delaunay graph, which basically is you build a Voronoi diagram and then you connect up all of the points in the Voronoi diagram. This is a planar graph, so it has average degree at most 6. So in 2 dimensions, sparse navigable graphs, sorry, it's planar, but it's also navigable. The Delaunay graph is navigable. You can prove that. And it's planar, so it has a degree of 06. Our total degree for the graph would be like order n. In higher dimensions, there's a really interesting paper by Arya and Mount from Soda 1993, which proves that you can always find a navigable graph with degree 2 to the d. So your total number of edges would be like order n times 2 to the d, which is cool, but in our setting, it's sort of meaningless because like d is so high. Okay, here's what I claim. This is a very easy thing to prove, but the technique is going to be important for understanding other stuff on the top. Any data set, x1 through xn, emits a navigable graph with average degree 2 root n under any distance function. Doesn't even need to be Euclidean. And because it's any distance function, importantly, it can be Euclidean distance in any arbitrary dimension. So there always is a sparse navigable graph. Yeah.
The same graph works for all distance functions?
No, you need to choose the graph dependent on your distance function. You fix the point set, fix the distance function, and then you produce the graph. But you can always get one that has like significantly less than linear sparsity. So the average out degree is just root n. Okay, we're gonna prove that. We'll give a slightly weaker proof. So we'll prove that you can get one with degree root n log n. And then it turns out this is actually optimal. So in a NeurIPS 2024 paper, we showed that even if you take random points in log n dimensional space, the sparsest navigable graph for those points has degree, like average degree, roughly n to the 1/2, like n to the 1/2 minus epsilon. Yeah.
So this is without any.
This is without adding any auxiliary vertices, which, by the way, is an interesting question. So in practice, people don't do any Steiner vertices or stuff like this. But I'll say it at the end of the talk. It's one route that you can hope to improve algorithms is by adding auxiliary vertices. It hasn't really been explored.
For something like this, you can lazily just cheat by creating a cloud around the recursion.
Yeah. For some, yeah. You can, if you just care about navigability, but if you just care about navigability, it's sort of too easy. But if you want to solve the problem of actual approximate nearest neighbor search, where you get like multiplicative approximation, we don't solve that with navigability. It could be helpful. Yeah.
Shouldn't you think it's like local? Because when you mentioned small world in the beginning, there are these long links. We also need that as like the initiation.
You'll see it's going to show it's going to have both. The graph that yields this is going to have both a lot of local connections and some random long range connections. Okay. Any other questions about the result? Okay, yeah, you'll see the construction in 1 second. I want to just give a slight, this is not really a different definition, but it's different enough that I think we need to process it. So the way I define navigability initially was, I said, greedy search started from any point needs to converge to any target if the target is in the data set. There's a much simpler way to think about this as a local condition. So in particular, an equivalent property, this is just a different way of stating navigability, is take any I and any node j, which is not I. Navigability demands that I has some out neighbor k, which gets me closer to j. So for which the distance between j and k is smaller than the distance between j and I. That out neighbor k could be j itself, right? In which case the left-hand side would be 0, or it could be some other node that gets me closer. That's equivalent to navigability, because if this is true, greedy search always has a way to make progress. If this is not true, it's easy to come up with an I and a j where greedy search stalls and it doesn't actually find a j. Okay, to avoid weird tie-breaking stuff, I don't want to think about what greedy search does if it has two distances that are the same. So let's just assume that all distances in the data set are unique. There's no like actual which in practice is fine, you add a small amount. Okay, so that definition is equivalent to navigability. So let's just do a picture on this. Here's a graph. Is this graph navigable? Let's pick an I and a j. Is this graph navigable from I to j? Yes, because you can choose k equal to 3. K gets you closer to j than j was to I. Okay, it needs to hold for all pairs. So let's pick I is over here and I is 3 and j is 2. Now, I's only out neighbor is 4, actually, which does not get you closer to 2. So this is, you don't satisfy that condition. So this graph is not navigable because I can't greedily route from 3 to 2. But you could like add a back edge from 3 to 2 and now suddenly the graph. Okay, so that's the picture we're going to have. Okay, so how do we construct a navigable graph? To think about how to do it, I said we're going to add like long range and short range connections. I want you to think about something I'm going to call the distance-based permutation matrix. This is really simple. For every node is corresponding to a data point. The first node to data point 1. Take all of the other data points and sort them in order from their distance to node 1. So 1 is the closest thing to 1, right? Then maybe 10 is its second closest neighbor, 2 is its second closest, so on and so forth. And do this for all nodes. 2 is the closest thing to node 2, 4 is the second closest. Produce this n by n matrix that shows these permutations. Okay, and now to think about how to construct a navigable graph, what I'm going to do is when I add an edge from node 4 to node 9 in the graph, or in general from node I to node j, think about that edge as being added to every row in this distance-based permutation matrix, pointing from 4 to 9. Okay? I do that for all the edges in my graph. I claim that the graph is navigable if for every element in this distance-based permutation matrix, it has at least one edge pointing to the left in every row. Because what does that mean? If I have an edge pointing to the left in every row, I can get closer to node 1, I can get closer to node 2, I can get closer to node n. Yep. Okay, got it? So now here's how we're going to use this. We're going to do a union of two graphs. Choose some m, which is going to be less than n. Ultimately, m is going to be something like square root of n. Okay? Add an edge from j to I if j is one of i's m closest neighbors. So in particular, look at the left part of this matrix, the first m columns. I should add an edge from all of the elements in those first columns directly to node 1, okay? Or node 2, just like this. I add those to the graph. So by the way, what that means is like when I add 10, 1 to the graph, it doesn't really just get added to that row. I add edge 10, 1 to the graph. That also means it gets added to like the second row and the last row. And same with 2, 1, it gets added to all those rows. So there are other edges floating around here, but I'm just going to think about the ones in the that are like within that first column. But that's what I mean by like if 10, 1 appears here, add the edge. If 2, 1 appears, add the edge. Does that make sense what I'm doing? Okay, and then the other thing we're going to do, it's ridiculously simple. Add order n over m times log n, uniformly random out edges to every node. Just pick a bunch of random neighbors and add out edges. So this looks like neighbor 9 got connected, node 9 got connected to 3, 4, 7, and all of those different rows. Okay, probably some of you can already see why this produces a navigable graph. So what's the analysis? We need a left pointing edge from every point in this distance-based permutation matrix. We trivially satisfy that for all of the elements in that first part of the matrix, and we only added n times m edges at most to add those edges. Okay? On the other hand, if you're at a point here, not in that first region, not in that shaded region, what is the chance that a random edge lands in the shaded region? It's at least m over n. The worst it could be is if you're 5. You're like right at the edge of the shaded region, then most random edges point to the right, and only m of them point to the left, so it's m over n. It could be a lot better. If you're midway through, it's like a 50-50 shot left. But the chance you have an edge to the left, if you're not in the shaded region, it's at least m over n. Okay, so that means that if I take n over m log n edges, the chance that I have no edge pointing to the left is extremely small. It's like 1 over poly n, so it'll definitely have an edge pointing to the left of that. Okay, so that's it. I satisfied all my constraints. The total number of edges I added was nm, plus for every node I added n over m log n random edges. You minimize that sum by setting m to square root n log n, and then you get a graph with average out to root n log n. Okay, so it's a super simple construction.
Yeah, only 2 blocks away.
Yeah, that's a great observation. So I thought I wrote that somewhere. Yeah, so it's also low depth. So it's only with high probability you can get to anything in 2 hops, which is pretty like a close line.
So this qualitative is very similar to this correction to the Watt-Strogas model due to Kleinberg.
Yeah, so this is inspired by that. So actually I skipped the slide, so let's go to it. I won't define that model, but basically people were interested in small world graphs and making them low depth. And people like John Kleinberg studied them in low dimensions and actually just points on the grid. And the suggested construction he had, which is like what you're suggesting as well, is you do a bunch of local connections, like you connect your neighbors in the grid, and then you do some long range connections. He builds sort of like a skip list type thing. This is exactly the same idea. So there's nothing special going on here. You pick a point, and basically I drew it. You have the local connections are caused by the nearest neighbors here. It's not exactly as I drew it. Technically, it's like you are connected, you get edges from all of your nearest neighbors. And then for every node, you also add a bunch of long range connections. And it makes sense why this works for search. If you're far away from a point, a long range connection will help you get there very fast. And then these local connections let you explore the region around the point to actually find them. So it's very intuitive and sort of actually aligned with what people do in practice. Like the graphs that people use in practice, they build k-nearest neighbor graphs and add random edges. That's basically what this is. So it's like, yeah. We were a bit surprised. I mean, the proof is, as you guys can see, it's very easy. We're a bit surprised that you can just get the sublinear degree so easily.
So you did not even use, so this just went for arbitrary permutation rows, right?
Yeah, you don't even need a
Yeah.
metric. Like, yeah. Mhm. Like any distance function. Yeah, technically this it requires yeah. You it's the tie breaking thing gets annoying. If you can have repeated distances in your data set, then the definition I'm using here doesn't cleanly match onto what navigability maps onto. But that's just assume that you have unique distances.
Look at that too, which is the best we can do.
Yeah, exactly. Yeah. Okay, so that's the construction. Yeah, I maybe what I was gonna briefly okay, I talk about this. This is optimal. So you can't, there are data sets even in low dimensions and login dimensions where you can't do better than root n. Maybe I'll give you like a super brief sense of why that's the case. I'm just going to give you like a proof sketch, and then I want to talk about the other stuff. So yeah, I'm going to look at this distance-based permutation matrix, and we basically have root n edges coming from both our random edges and from our nearest neighbor edges. I'm going to claim that root n degree is required just to cover these like nearest neighbor sort of constraints. The fact that you need left pointing edges in that box. Okay, how do you do that? This is very sketchy, and this is actually like the core of the paper, so it's hard to prove, but it's intuitive. If I pick random points in log n dimensions, you can actually show that these permutations lists, those left lists, they essentially look IID uniform random. So even in log n dimensions, those lists essentially look like you just put, okay, the first thing is always 1, but then this would just be like root n random things. First thing is 2, but then this would just be root n random things. Even in log n dimensions, that's basically what they look like. If that's the case, that takes effort to prove, but if you can prove that's the case, then it becomes clear that root n dimensions is root n edges is required. Because in particular, pick any jk. If I have an edge between j and k, the chance j lives in one of these rows is 1 over root n, if it's that row I'm modeling as random. The chance k lives in one of those rows is also 1 over root n. So the chance both j and k live in the same row is roughly 1 over n. That means that with high probability, the number of rows any j and k will appear in together in the left region is like log n. So if you add an edge from j to k, you can only kill off log n of the constraints you need to satisfy in that left region. You can only get at most log n left pointing edges, and that's being optimistic. So basically that tells you that you can't do better here than root n over log n. So that's like a lower bound and it even holds for random points. Okay. Yeah, so takeaway. In the worst case, omega and n to the 3 halves edges, so that's n to the 1/2 average degree, are sufficient to construct a navigable graph, and they're necessary in the worst case. But the worst case is for random data sets. And you might think that data sets in practice don't look random. Okay, so a natural hope here is, could we do better for data sets in practice? And you can frame this instead of as an existence question, you can frame it as an optimization question. So natural question is, you give me a data set, how quickly can we construct the sparsest navigable graph for that data set? Yeah, can I do that efficiently? And here I'm going to give up about worrying about things like depth. So I'm just going to worry about sparsity because it's like hard enough to do sparsity, but if you want a problem, you should also think about depth because it obviously is important. Okay, so yeah, this will put me in the next part of the talk. Let's talk about this. This result we published at SOTA this year. So the claim is as follows. For any data set in any distance function, so again, it's just based on permutation, it doesn't require metric or anything like that. It's possible to construct a navigable graph with at most order log n times the optimal sparsity in nearly quadratic time, so in order n squared time. I'm not counting the cost to compute distances. So what the dominant cost here is I need to compute all pairwise distances. So I'm thinking of d as a constant. But you can compute a near optimal sparsity graph in quadratic time, nearly quadratic time. Okay, so yeah, this is optimal. You can show that you can't do better than quadratic time, where you'd violate the strong exponential time hypothesis. Basically, just like a one-line reduction to the monochromatic closest pair problem. you can't obtain better than a log n approximation in polynomial time. Like that's an NP-hard problem. You're going to see because there's a connection to the problem we're solving in set cover. So that's the two things I'll mention. And then the other thing I'll mention is like we actually had there was a simultaneous submission to SOTA that proved almost the same result using like similar-ish techniques, sort of different techniques by Kana, Padaki, and Weingarten. So that's another paper to check out on the top. Okay, let's talk about how we do this. How do we construct sparse and navigable graphs? There's a very easy connection to set cover. This is just, you can just view this problem, this navigable graph construction problem, as n different set cover problems. Let me explain how we can do that. So the point here is for any node I need to find an out neighbor k, which covers any other node any other node j, in the sense that k should cover j if k gets me closer to j. Okay? So fix a node I. Let's say my node I is 1. If I draw an edge from 1 to 3, drawing that edge gets me closer to not just 3, but it gets me closer to node 2, node 3, node 4. So I'm going to think of that as there's a set, which I label as set edge from 1 to 3, which contains nodes 2, 3, 4. I satisfy the constraint of getting closer to 2, getting closer to 3, getting closer to 4. Similarly, if I draw an edge from 1 to 5, I get closer to 4, 5, 6. That gives me another set. I get one of these sets for all things I could possibly draw an edge to. And then our goal is to find the smallest number of out neighbors for I that covers all of my points. So it's just a minimum set cover problem. Okay, so that's the starting. Once you see it's a minimum set cover problem, actually maybe I'll dwell there for a second. Is it clear why it's a minimum set cover problem? You have one for every node in the graph. Okay. Once you see that, you get a really easy cubic time algorithm. In particular, you can check that you can just write down all of these set cover instances in n squared time each, and there are n of them. There's one for each node. So you get an n cubed, you get like n squared size set cover instances. You can run the standard greedy algorithm for set cover. So the greedy algorithm for set cover says just pick the set that covers the most objects, delete those. Pick the set that covers the most of what remains, delete those. Pick the set that covers the most remains. That is a simple algorithm that gives you a log n approximation to the minimum set cover. You can run that in linear time and the size of your set cover instance. So overall, we'll take n times order n squared time. It'll take us like n cubed time to find the near minimal sparse navigable graph. Okay, so just to give that in pictures, here 4 is the node which covers the most things because it gets me closer to like 5, 6, 7. Delete all of those 4, 5, 6, 7. Now either of those options are good greedy options. 2 doesn't get me closer to 1, 1 doesn't get me closer to 2. So I pick either of them, pick 2, and then I pick 1. That's the greedy algorithm, and that will give me competitive with the best set cover. Yeah.
And this n cube is dominated by writing down the problem.
The n cube is dominated by writing down the problem. Exactly. So to get
and an implicit data structure.
Yeah, which is exactly how we're gonna do it. So we're gonna have to. Okay, we're gonna do it with two things. We're gonna do it by writing down an explicit a data structure that lets us do better. That'll get us like half of the way there to like n to the 2.5, and then we'll do better with another trick. Yeah, good observation. Yeah.
And so for the minimality here, like it's for my the number of edges.
Mm-hmm. Yeah.
I chose 4 that are not 5.
Yeah, exactly. So this greedy algorithm always gets within log n of the minimum number of edges you needed to cover the points. Yeah, so as Mark noticed, like the bottleneck here is just writing down the set cover instances. So how are we going to beat cubic time? We have to avoid writing them down explicitly. So we're going to try to construct a data structure that gives us Oracle access to information about the set cover instances more efficiently. Okay, so here's what we can do. What's the data structure we're going to construct? We're actually going to construct this exact same distance permutation matrix that I introduced earlier. How long does that take to construct? It's basically n squared times log n time. For each node, I need to sort the other nodes with respect to their distance from that node. So I just run n sorts, and then I put those nodes into the data structure. So I build that. What-
We are
Right.
hiding all the poly detail.
I'm hiding all the D factors. It's actually all linear in D, but I'm just hiding it. So yeah, assume it's constant. Okay, so what does this distance-based permutation matrix let me do? It lets me answer two things about my set cover instances efficiently. So in particular, it lets me answer membership queries. So a membership query says, we have a bunch of set cover instances, n of them. Is node J in set K in instance I? What that is asking is dj k, so the distance from J to K, smaller than the distance from I to K? How do you do that? We just look in the row corresponding to J, and you check, does K appear first in the row, or does I appear first? If K appears first, it gets me closer to I, so I am in that Kth set in instance I. So that's one thing it lets me answer. It also lets me answer set of queries. So a set of queries of the form, what is the Kth set containing J in instance I? So how do I do that? Well, what are the sets that contain J in instance I? I look at the row corresponding to J. It's a little bit weird because the instance doesn't correspond to row. Look at the row corresponding to J, and then say I is 10. All the sets that contain J in instance I are the Ks that get me closer to I. It's everything to the left of 10 in the row. And I can just store like an inverted index so I know where 10 lives. So I can just read those off, and do that in linear time. Okay, so those are called set of queries. We have membership queries. Okay, so fortunately, there's been prior work on understanding can you efficiently solve set cover problems approximately if you only have query access to the data structure. This work actually allows for a different type of query, which they call an ELT of query, which is basically you input a set and then you get all of the elements to it. We didn't do that. We input an element and you get all the sets that cover it. But if you squint hard enough and you do some work, you can see that like modifying these algorithms can immediately get us an algorithm that runs in n to the 2.5 times. So I'm not going to talk about the machine learning algorithms, but like you can do something there. To reduce this to quadratic, we need a different approach. So I have 10 minutes. Let's see. We wanted at 120.
Yeah, like 120.
Yeah, I think I can do this. So I'm going to try to, okay. We have an algorithm. Our algorithm is like a sublinear time set cover problem. So it solves the problem that these guys solved, but in a rather different way. I think it's in a simpler way, but that's up for argument. The main reason we're doing it in a different way is because we couldn't figure out how to squeeze. We can shave an additional n to the 0.5 off our algorithm, and we couldn't figure out how to do it for their algorithms. I'm not saying it can't be done. So the first thing I'm going to do is present an algorithm that is not new. It's not like it's new, but doesn't give anything better than the prior work. And then we're going to show how to shave an additional n to the 1/2 off of that. And that algorithm is really simple. The way we're going to do it is we're going to directly simulate the greedy set cover algorithm. So let me describe how we do that. How do we simulate it? I'm going to show the simulation for my instance of set cover, which is this navigable graph problem, but it applies to any set cover problem. It's not specific to this instance. So in my instance of set cover, I have the starting node I, and my goal is to choose out edges. The out edges correspond to sets. How do I pick what out edges to include? Well, ideally, you want to include the out edge, which covers the most number of things. I'm going to, instead of computing so the way you would do that is you go through all possible sets and you check how many elements do they contain. I'm going to instead approximate the number of elements that are contained in the sets via sampling. So in particular, I'm just going to start by sampling elements, which in our case are uncovered nodes. And we're going to think of those ones I sample, we're going to call them voters. Okay, so I sample a random uncovered node. And then what I do is I check what sets contain that node. I can do that efficiently because I have set of queries. By sets that contain that node, in this problem, that means any point that would get me closer from my start to that node. And I maintain a table where I just add a counter for each of those sets that contains the node. I sample another random element to be covered, and I increment my counter for all the sets that contain that node. In other words, all the points are going to be closer to there. And I keep doing this, incrementing my counters. Okay, keep doing this. At some point, I've done this a bunch of times. Here I've sampled 5 nodes. This element is starting to look pretty good. It covered 3 of the elements I sampled, whereas all of the other stuff covered almost 2. And what you can prove is that if you wait until a node obtains roughly log n votes, then with high probability, it might not be the set that covers the most things, but it'll be the set, it will at least cover like a constant fraction of the most things. It'll be competitive with the best set. So you just wait. You wait till your counter hits literally log n, and then you pick that set. So in this case, I would pick 3, which means I draw an edge to 3, and I cross out all the elements that 3 covers. I didn't do one additional cleanup step. So this node, it has a vote of 1 because some of the stuff, like one of my sample nodes, it got me closer to that sample node. That sample node not just got covered, it got deleted from the instance. So I need to clean up by removing its vote. But that can be done efficiently. There's an efficient way to just like undo the votes you have. Okay, does the procedure make sense? And then I'll go through the complexity of the procedure. Okay. So what's the procedure? If you analyze the running time, the dominant costs are 2 things. The voting. So in particular, when you sample J as a voter, you need to find all the sets that contain it in the instance. We can do that like efficiently in that we can do that in linear time in the number of sets that contain it. But it could be that there are there could be up to like order n sets that contain it. So that takes like order n time. Okay, at least it's like linear number of sets contain it, but it could be up to order n. And then there's this element removal step. The element removal step is trickier because we don't have these LTOF queries. Like we basically, the only way to do that is you look over all uncovered nodes and you check were they covered by adding that thing. So that takes another order n time. So what's our total cost for the algorithm? Well, you pay these costs. You pay the voting every time you sample something. You remove an element. Basically, like every time something hits, you've done like log n increments to my voters. So you pay the voting cost roughly opt log n times, which is the number of sets I'm going to add to my approximate solution. And you pay the element removal cost roughly opt I log squared n times, because I only remove an element if it hit log n votes. Okay, so the total cost for this algorithm ends up being roughly, opt I times log n or times log squared n times order n time per each one of these updates. So I get an algorithm that runs in O tilde opt I times n per node. Opt I, maybe I didn't even say it, sorry. Opt I is the minimum out neighborhood size for node I, okay? If you sum this up over all the nodes, I'm going to use opt to denote the sum of the minimum out neighborhood sizes. So the total runtime of the algorithm is O tilde opt times n, which actually matches like what the prior working sublinear set cover is doing with this like very simple algorithm. Okay, and importantly, opt for the navigable graph, we proved it was no more than n to the 1.5. So this is n to the 2. Okay. Let me conclude by just giving you a very brief idea of how we get down to quadratic time. This is specific to this problem. So we can't get down to quadratic time for general set covers, sequences of set cover instances. This is just for this set of n set cover instances. We basically do a pre-processing step. And the pre-processing step, it's intuitive. We saw it earlier. Adding random edges to a graph is a really effective way to cover constraints for the navigability problem, because like it's a good chance that a random edge is going to get me closer to at least a large fraction of points in the data set. So what do? We add a bunch of random edges to start, and we can afford to add roughly opt over n random edges to every node in the graph without increasing my degree too much. What does that do? It has 2 impacts. First off, any element which is contained in a lot of sets, meaning there are a lot of edges that get closer to it, will get covered by a random edge with high probability, because you're likely to be in one of those sets. So in particular, I'm choosing opt over n random edges. Any element which is contained in greater than n over opt-n sets will get covered by those random edges. So anything that's left is contained in at most n squared over opt sets. Opt is always greater than n, so that's like better than n. That's going to improve our voting cost, right? Because when we voted, the issue there is I could have been contained in up to n sets. After this random pre-processing, that won't be the case. You'll be contained in at most n squared over opt, which is less. And then moreover, this is actually true for general set cover instances, so you can use that trick in general. Yeah, moreover, in this navigability problem, we said that if you had random edges, you will basically cover all of the constraints on the right part of this distance-based permutation matrix. You will only not cover the constraints in this region, where like the width of that region, if I add opt over n random edges, is roughly like opt over n. So it's like opt over n squared. You don't cover, oh no, it's 1 over that, I'm sorry. N over. The total number of constraints you don't cover by these random edges with high probability is n cubed over opt across all of the instances. And what this means is it makes element removal faster. So you do this pre-processing step, it's very cheap to check what you covered, and then you don't need to worry about removing those elements from our sublinear set. Okay, that's the level of detail because I'm basically out of time that I'll leave that at. That basically reduces the cost. So very quickly, what was our total voting cost? It's the number of voters you had, which is O tilde of opt-I, times the cost to increment my votes, which we just said we reduced to n squared over opt. Let's make things simple by assuming that opt-I is roughly order opt over n. So assume my out neighborhoods are roughly the same size for all nodes. Then the calculation is really easy. You get opt-I times this becomes n over opt-I, which is order n. Doing this when you can have out neighborhoods of very different sizes is actually a lot trickier. So there's like a lot of work that goes into that. We have to do a different pre-processing technique, but this is the gist. And that gives you like the final quadratic runtime. Okay. Can I really quickly do some open questions? We're at 120. I'll be really quick. So yeah, okay. First off, what do we want to do? So the recap is all data sets have at least reasonably sparse navigable graphs. We now know how to construct near optimally sparse navigable graphs in sort of like almost the best possible time you could hope for this problem. So where does this leave us in terms of understanding graph-based methods? Importantly, I think it's obvious to you guys we talked about earlier, this does not solve the problem of like getting LSH style guarantees for graph-based search. There are two barriers there. First off, we proved that navigability, or we saw that navigability guarantees you always route to a query that is in the data set, but it can lead to arbitrarily bad results for queries that aren't in the data set. So here's a navigable graph. 1 can get closer to 3 to 2 to 3, 2 can get closer to both. This is a navigable graph for 3 points, 1, 2, 3. Imagine this query, and imagine I started at node 1. 1 has no edge that gets me closer to the query, so I will just stop at node 1. I will never go to node 2, and therefore I'll never make my way to node 3. If I stretch my iPad like as much as I want, I can get an arbitrarily bad approximation factor. So that's one issue. So what are ways to get around this? There's an interesting notion, a generalization of navigability called alpha reachability, which is stronger. It says that instead of needing an out neighbor k that gets me closer to any target j, I need one that gets me significantly closer. So there's some parameter alpha, and I want to get significantly closer. So like if alpha's 2, I want a k that covers half the distance. This property was introduced because people were thinking, oh, that would make convergence of our search faster. But interestingly enough, you can use that property to prove an approximation guarantee. So any graph with the stronger notion, alpha reachability, gets you an alpha plus 1 over alpha minus 1 approximate nearest neighbor, which is pretty cool. This was proved in a recent result by Indig and Ju. We're interested in constructing these stronger notion navigable graphs faster. So there's an algorithm, both in our paper and this paper by Khanna, Padaki, and Weingarten, that runs in n to the 2.5 time. And then under a slightly weaker notion of like a bicriteria approximation, I won't go into the details, they get an algorithm that runs in n omega time, where omega is the matrix multiplication exponent. Can we get n squared time? It's like a very natural question for that. And then
This first question might require now restricting to L2 or something. Like,
I would be fine if you're restricted to L2, yeah. Yeah, that would be totally fine. Ideally not in low dimensions. So like ideally in something greater than log n dimensions, but yeah, that would be totally fine. Yeah, that is one that we're interested in. Yeah, the other thing is we skipped two things. First off, we didn't bound the depth of our search paths in our graph. Second off, we focused on average degree. We didn't actually prove that these graphs have low maximum degree. So that's a problem. You can very easily construct data sets. An example is take the origin and then a bunch of standard basis vectors. And if you want it in low dimensions, project it down with JL. The origin is the nearest neighbor to all the standard basis vectors. So in a navigable graph, it must be connected to them. So this is a point set, easy to construct, where the best navigable graph has maximum degree n. What if you routed through that point? You would be screwed. Then you'd have an n times search. So the other thing we're really interested in is how do we actually translate this into efficient search bounds? And there's a lot of possible directions here. I think like people who work in this area would say, well, we've never seen that in practice, so just assume it away. Like just that's not going to be true. Don't worry about it. But if you're a theory person and you're worried about it, there's a lot of things you consider, like possible variations of greedy search, like backtracking search. To Mark's point, you can ask if you can do better by adding Steiner nodes to the graph. Can that help you reduce maximum degree? Yeah, a bunch of other stuff like that. So I'll leave it at that. Thanks, guys. Yeah.
do they work? Did you try it like running?
Does our construction work?
Yeah.
It's too okay. This is another good question. N squared time is too slow for that. So the algorithm, for a billion points, you can't run it. What we did do is we ran it for billion point data sets for single points in the data set just to see like, do these data sets even have sparse navigable graphs? And they have very sparse navigable graphs, like degree 100, roughly. And the graphs people produce in practice have degree like 64. So it's like, yeah, but we can't run on the whole shebang because it's too slow. But another cool question is, if I assume my data is in low dimensions or low intrinsic dimension, can I produce a navigable graph in sub-quadratic time? So our quadratic time bound, like you need your points to be in log n dimensions. It follows from like a monochromatic closest pair. But what if your points had like constant intrinsic dimension, like doubling dimension? Could you get better than? I already have. There's some like progress on that, but that's a good direction.
Actually, one more related question.
Yeah.
So you said that these embeddings are generated by BERT or
Yeah.
So, like, I have two questions about it.
Yeah.
Is that efficient? Like, can you actually, if you replace Google search algorithm by step one, compute the BERT embedding of the query vector that I sent? Is that's
efficient enough? Yeah, it's because it's just one vector. Yeah, and the way, they get that efficient enough that the model, since everyone is querying, these models are deep networks, but they're pipelines. So like, as soon as my vector goes through the first layer of the network, another vector goes through
simultaneously.
Yeah, so the layers of the network are stored on each one stored on a GPU, and basically it's like instant time for that. Yeah, so they can afford to do this.
And then do they? So you said that they have some locality property that you transform similarity into some metric. What's the metric that these models?
Well, the models are, what are the models trained on? I think it's usually inner product because it's cosine similarity. And then when they do search, it's also cosine similarity. Yeah. But actually, I forget if I'm not sure that the embeddings are themselves normalized. So it's cosine similarity, so it's not exactly inner product.
Yeah, normalize the vector to the unit and then take data.
Yeah. Yeah, thanks, guys.
Thank you so much.
Yeah.
What one year schedule